Welcome to the new era of video creation with BioZ8. We will discuss with how do you approach model evaluation and selection for machine learning models? Can you explain various metrics and techniques used to ensure that the model performs well? Here is the content. Model evaluation is crucial in machine learning as it helps assess how well a model performs on unseen data. The objective is not only to determine how well a model fits the training data, but also how it generalizes to new, unseen data. To evaluate a model, various metrics are used depending on the problem: classification, regression, etc. Accuracy, precision, recall, and the F1 score are common in classification problems. For regression, metrics like mean squared error, MSE, and R2 are more applicable. Additionally, techniques like cross-validation and grid search ensure that the model is robust and optimal. The goal is to ensure that the model can perform well on real-world data and does not overfit or underfit. When working on classification problems, the following metrics are essential for evaluation. Accuracy is the simplest metric. It's the proportion of correct predictions out of all predictions. However, accuracy might be misleading in imbalanced datasets. Precision focuses on the positive class and is the proportion of true positives among all predicted positives. High precision means fewer false positives. Recall is the proportion of true positives among all actual positives. High recall means fewer false negatives. F1 score combines precision and recall into a single number by taking their harmonic mean. It's particularly useful when the dataset is imbalanced, providing a balance between precision and recall. These metrics help determine the suitability of a model for imbalanced classes or situations where one error type, false positive or false negative, is more critical than the other. For regression problems, we evaluate models using different metrics. Mean absolute error, MAE, calculates the average of the absolute differences between predicted and actual values. It's easy to interpret but does not emphasize larger errors. Mean squared error, MSE, squares the errors, so it penalizes larger errors more. It's more sensitive to outliers. Root. Mean squared error, RMSE, is the square root of MSE, giving it the same unit as the target variable, making interpretation easier. R squared, R2, is a statistical measure representing the proportion of variance explained by the model. It's a standard metric for evaluating regression models. Each of these metrics provides insight into how well the model generalizes and how accurate its predictions are. Cross-validation is a powerful technique used to assess model performance more accurately. The most common form is k-fold cross-validation, where the dataset is divided into k subsets, or folds. The model is trained on k1 of these folds and tested on the remaining fold. This process is repeated for each fold. Cross-validation provides a better estimate of model performance because it ensures that each data point gets used for both training and testing. This method helps reduce overfitting and provides a more reliable evaluation of the model's ability to generalize. If the model performs consistently across all folds, we can have higher confidence in its performance. The holdout method is a simple evaluation technique where the data is split into two sets, a training set and a test set. The model is trained on the training set and then evaluated on the test set. This method is quick and useful for large datasets where splitting does not significantly impact model performance. However, it can be prone to overfitting or underfitting if the test set is not representative or the data is too small. To mitigate this, it's often combined with cross-validation. Hyperparameter tuning involves adjusting the parameters of a model to improve its performance. It can significantly impact model accuracy. There are several methods for tuning hyperparameters. Grid search is an exhaustive search over all specified hyperparameters. While it can find the best parameters, it's computationally expensive. Random search randomly samples from the hyperparameter space. It's more efficient than grid search, especially when dealing with high-dimensional spaces. Bayesian optimization is a more sophisticated method that builds a probabilistic model to select hyperparameters. It uses previous evaluation results to make informed choices about the next hyperparameters to test. Hyperparameter tuning helps improve the model's generalization and performance. One of the most critical aspects of model evaluation and selection is understanding the bias-variance trade-off. Bias refers to errors introduced by overly simplistic models, which may not capture the underlying patterns in the data, e.g., linear regression on a non-linear dataset. Variance refers to errors due to the model's sensitivity to fluctuations in the training data, often leading to overfitting. The trade-off means that increasing model complexity, e.g., using a deep neural network, can decrease bias but increase variance. The goal is to select a model that balances bias and variance, minimizing the total error on unseen data. Once you have a selection of models, it's important to compare their performance. A/B testing compares two models by evaluating them on the same dataset under identical conditions. Validation curves allow you to visualize how a model's performance changes as a hyperparameter is varied, helping identify whether a model is underfitting or overfitting. Learning curves help analyze how the model's performance improves as more data is added, or the model is trained for more iterations. For model comparison, it's essential to establish a robust evaluation framework based on the business problem, ensuring the chosen model aligns with the objectives. Overfitting and underfitting are two common problems in machine learning. Overfitting happens when a model learns not just the underlying patterns, but also the noise in the training data, leading to poor generalization on unseen data. It can be prevented using regularization techniques. Underfitting occurs when the model is too simplistic and fails to capture important patterns in the data, leading to poor performance on both training and test data. Regularization methods, such as L1 not L2 regularization or dropout in neural networks, can help reduce overfitting by penalizing large model parameters. Cross-validation helps identify overfitting by providing a more accurate estimate of model performance across different subsets of data. In conclusion, model evaluation is an ongoing process that continues even after the model is deployed. Continuous monitoring ensures that the model remains effective over time and adapts to any changes in data. Model monitoring helps detect any performance degradation or data drift, ensuring the model stays relevant and accurate. Choose evaluation metrics that align with your business goals, ensuring that the model performs well for the end users. Regularly update and tune models as new data becomes available, keeping them competitive and accurate. Evaluation is not just about accuracy. It's about the entire process of selecting, testing, and deploying models to meet real-world needs.